Today, we will be talking about the designing of the ANN by the use of Matlab, and we will find out where to use it. So, uh, so why I have chosen Matlab is for the fact that Matlab for the beginner is a very comfortable and user-friendly software tool, a complete package. And now in the latest 2020 version, Matlab has turned out to be very versatile and very uh, comfortable for the beginner also and for the very professional. It gives lots of flexibility. Its compilers are now sound based on DC++. And lots of support comes through the documentation and presentations, visual presentations. So therefore, I thought since there are masters and PhD students, therefore for them many will be quite familiar with the MATLAB, but there might be beginners. Therefore, I thought a brief familiarization with the MATLAB is required. Then we will shift to how to design the ANN by the use of the MATLAB. So the plan of presentation, a few slides regarding the MATLAB, basic considerations of design of a perceptron, multi-layer perceptron, and design, and a few notable applications with the ANN and its use in the MATLAB domain. So this shall be our plan of presentation today. So with this, these slides I shall be sharing. So I have placed here a few codes. Since I shall be sharing the slides, so you can take them and then try to practice. These are all found in the MATLAB documentation, so it's not that restricted. These are all taken from the MATLAB documentation, so you can also see it from the MATLAB documentation, but try. So here this picture sums up why we need the MATLAB. Since a picture sounds 1,000 words, and that is the basic philosophy behind which the MATLAB tool functions, or MATLAB tool has developed. So it was since we all know that that our brain is based on 50% visual processing. 70% of all our sensory receptors are based on the eyes, and we can get a response from a visual stimulus in just about 0.1 seconds, so one tenth of a second. So it's quite, our brain is quite comfortable with the visual part, visual presentation. The strength of MATLAB lies in its visual presentation. Therefore, people around the world have been sticking to the MATLAB domain, though it's quite costly. MATLAB is the product of the mathwork.com. So it's a versatile yet and the most preferred test and validation software around the world for students, for faculty members, for the practitioners, for the professionals. MATLAB is derived from two words, matrix, laboratory, and all of the MATLAB's computation is based on the matrix consideration. So scientific and the engineering, numeric computation, and visualization, these are all based on the matrix concept. So where you can use it in all domains: mathematics, computation, algorithm development, data acquisition, modeling, simulation, prototyping, analysis, exploration, visualization, scientific and engineering, graphics, and you just go on naming. In all these domains, you can use the MATLAB tool. So MATLAB was launched in the 1970s. Dr. Clever Moller. The first version, MATLAB 1.0, was based on C. 1990s saw the launch of the MATLAB based on the Windows. Then Simulink, notebook, symbology-based computation came to being slowly, and then the 21st century versions turned out to be very, very widespread, robust, versatile. So here you have powerful tools for matrix calculation. Basic data type is a double complex matrix with a subscript of 1. You have multi paradigm here. You have an interactive environment where there is no compiler, and it supports widespread programming. Most of the I/O parameters in the MATLAB functions are variables, user friendly. It will make the user quite comfortable while you start with, and therefore, since there is a spot-on reaction or a response comes in from the MATLAB platform, and in that very moment, so most of the people who start with MATLAB, most of the students who start with the MATLAB feel comfortable. Basic block diagram is something like this. There will be tools, the development tools for the applications. You have the toolboxes, you have data assessing tools, mainly to deal with the data. Simulink is one big component of MATLAB, where you have the state flow, state flow facilities. You have the module libraries. You have generating code tools. Previously, that was C. Now it's VC++, and then third-party modules are also supported. Then the structure of the MATLAB is based on the development environment, MATLAB mathematical functional library, MATLAB language based on C++ mainly, graphics, and the MATLAB application development based on a few APIs through which the codes can be developed and codes can be run also. Now the current version MATLAB, that is the 2020 version, that runs in a client server setup. So in a laboratory, normally there should be one computer that is configured to be a server where the license shall be deployed based on the TCP IPs, and then the client's link to the server shall be sharing the license. And normally it's quite costly. You can have a perpetual license, but it's quite costly for and mainly for the campus licenses. The price is high. Frequently, we find that the students go in for the cracked versions. The cracked versions have all the facilities, but when we go in for scientific computation, when we derive or we want very precise results, if we go in for a cracked version, the results might not be that much precise. That is the difference. But for the rest of the cases, you will have the same toolboxes, same facilities, and all those things that you have in a licensed version are same. But nowadays, MATLAB has turned out to be very strict in controlling the licenses. Here is the desktop logo, and that is when you start the MATLAB, you will look like this. You will see a screen coming that looks like this. You will have the toolboxes, the command history, then you have the current directory, you have the command prompt here. So from the command prompt too, we can start doing work with the MATLAB. We can also write program separately, but from the command prompt, we can straightway start to write our codes and do the work in MATLAB. So here is the command prompt. Here is the MATLAB menu bar, how it looks like. So there, from where we can save, you can create or manipulate the files. Toolboxes, there are more than 50 toolboxes, and the list of toolboxes are continuously growing day in day out. So those toolboxes permit us computation from all known domains of science and technology, social sciences, and so on and so forth. So it's quite flexible, quite covering, quite inclusive. Means all types of computations shall be supported by MATLAB. Very rudimentary calculation to very sophisticated scientific calculation. All things can be done by MATLAB. So you can do very simple maths, just going on typing in the command prompt, and then here no such requirement of prior variable declaration is done or is required in MATLAB. You can just say something like, say, a is equal to 5. That means a variable declaration. B is equal to 10. You can go on typing like that. No prior declaration. So all types of data are supported, like, say, integer, floating point, character, and strings. They are all supported, and all the integers come in varied form. Say the unsigned form, you can have representations of bit 8, bit 16, bit 32, so on and so forth. That can permit you to control the precision generated. So straightforward way to generate a graph can be to say call in the function, built-in function plot of x, that will generate a graph. Now the same graph in C or C might take say 2,000 lines of code writing. So here in this MATLAB, it's quite simple, 2 lines of code to generate a graph. So you can deal with the vectors part. Quite simple to create a string of vectors. So while you create a string of vectors, summation, subtraction, multiplication, all those things can be done very simply. So I think these are quite simple for you all. So let's come to the neural network part. So there, the main part of the MATLAB is that you have a huge set of built-in functions. You therefore need not write separate functions. You need not write separate subroutines as we do in C and C++. These built-in functions save our time. These built-in functions make the programming or system design much less time taking. And the time taken to do work in MATLAB and then generate the visualization, check the results, are much less compared to C and C++. So hence people fall in love with MATLAB while they start to work with it. The simplicity, the ease of doing work is due to its built-in huge collection of built-in functions. Library of the MATLAB is very detailed. So all types of libraries can be there, maths libraries, statistical libraries, signal processing libraries, your all types of control system libraries, all known types of domains shall have their own toolboxes, and when the toolboxes are there, the complete collection of library and the built-in function shall be a part of the MATLAB repository. So let's come to the design of the ANN. So how we can design it. So we have so far become familiar with how the ANN is formulated. We have gone through the basic theoretical requirements, the basic mathematical foundations we have become familiar with. So we can now deal with the design of the ANN by the use of the MATLAB. Now, since we know that in the feed-forward form, the ANN is quite popular and has found widespread popularity all throughout the world in all known domains. So therefore, today we will stick to this feed-forward structure that is primarily known as the multi-layer perceptron. So here we will find out ways and means how to simulate a ANN by the use of the software tools that is there built in the MATLAB tool. Then we will find out the basic functions that are used for training it, for simulating it, and for generating the response from a multi-layer perceptron. So we can here find out how MATLAB supports the design of a multi-layer perceptron, and subsequently we'll find out the ways and means of how to speed up the training of the MATLAB supported ANN. We have seen that the ANN's success is primarily due to its capability to learn, its capability due to do a mapping between the patterns and the classes, response classes. It shows us non-linear processing. Then it can carry out contextual processing, and it is quite fault tolerant, and it has a diversity of types and topologies that serves the purpose of real world requirements. Now, while we go through all types of neural structures, we will find that primarily there are two broad classes of One is the feed forward type, and the second one is called the feedback type. Now, in the feed forward type, there are two broad classes. One is the supervised class, and the second one is called the unsupervised class. Now, in the supervised class, we will primarily be going through in much detail through the multi-layer perceptron. That is the most common multi-layer perceptron that works on the least recursive least mean square optimization. And then we can call the multi-layer perceptron to be back propagation networks, because they are trained by the use of the back propagation networks. Then we can have one more type. And that type is called the unsupervised feed forward type. We will be talking about that also. We will learn about the learning vector quantization, and we shall talk about the self organizing map 2, the SOM. So these two, the learning vector quantization and the SOM, we shall be becoming familiar as the time goes by. And in the feed forward type, we will find out later on that the recurrent back propagation networks, that the recurrent networks are very much successful to in carrying out the temporal processing. Recurrent neural networks are very well suited for doing time-dependent processing, while the feed-forward structures are good in doing the pattern mapping. They are not that successful in doing the time-dependent processing. Now, for time-dependent processing, we need feedback networks. The recurrent neural networks are a type of feedback networks that have shown very successfully time-dependent processing capability. So therefore, for all time-dependent phenomena like time-dependent prediction, speech processing, forecasting linked to the stock market, financial system, banking, and so on and so forth, we find that the feedback networks are very successful, or the recurrent neural networks are very successful. So let's come to find out. So this is the basic Matlab structure. We have spoken about that, so we will not speak about that much. Just showing there for bring in the context, so that we can next go to find out the ways and means of how to design a perceptron by the use of the Matlab tools. So now since we know that this is the mathematical representation, why will be the response? There will be an activation function that will be summing up the weights multiplied by the patterns that are fed to the system, and the bias linked with it. Plus minus doesn't matter. So this will be the response generated by a perceptron. So in a much scaled up way, that will be the representation. Now this same logic is followed by Matlab 2. Now here we should remember that the Matlab supports a few activation functions like the hard limiter and the purelin. So how to generate the hard limiter function? So if we can take a vector here, n from -10 with gaps up to 2+10, we can generate a hard limiter function. We can generate a hard limiter activation function by writing like this. So this will create a hard limiter function, and that will be something like this. Same way, we can generate, we can use a purely transfer function, and can generate a purely linear transfer function by the use of the built-in function purelin. So here there is a built-in function purelin. So this particular built-in function purelin can generate the purelin activation that is required for the design of a perceptron, and later on multi-layer perceptrons. Same way, we can use the built-in function logsig and the tensig for generating log sigmoidal functions and 10 sigmoidal functions. Log sigmoidal functions will look something like this. There shall be a continuum of values between 0 and 1 that will have a structure of this type, and the tensig will have a continuum of values between -1 and +1. We can regulate the range also, but if we take a vector n from say -5 to +5 with a scale with a gap of 0.1, we can use the 10-sig function to generate a 10-sigmoidal function that will look something like this. Now to generate a perceptron, we know that the perceptron is a straightforward Matlab model that has the capability to learn, and its capability to learn is governed by the gradient descent function. That is the gradient descent weight tuning method. So how the weights will change, how the weights will be tuned to be in synchronization with learning process. That particular philosophy is governed by the gradient descent function. So here is how the perceptron learning rule is formulated, or how it is structured. These are the steps we have talked about it in details in the previous classes, so we will not spend much time there, just for doing the referencing and building up. So Matlab has one built-in function called the new p that can be used to say create a perceptron. So here we can simulate the digital OR gate by the use of a perceptron. So here we have shown how to generate a perceptron that will deal with ranges of values between 0 and 1, and it has weights of -3 and 2. So the p will be the pattern vector, and t will be the target vector. The function sim is used to simulate the results. So there the p is the pattern vector here. The pattern vector will take all the values that the logical OR function will have, 0 0 1 1 0 1 0 0. So that will come in combination of 0 0 0 1 1 0 and 1 1, that way. So here is the target. So this is the way how to formulate a perceptron. Net will be the variable that will hold. That is a structure variable that will hold the new p, that perceptron generated by the built-in new p function that is supposed to deal with values between 0 and 1 with weights of -3 and 2 with an output response node of 1. So there is one point where the response will be generated. So now this y is equal to sim net of p, net comma p will be simulating the result. Now if we write like this, we will not get the correct result, because now this net p new p that will be creating a perceptron structure that will be stored in the net variable. Now this particular net variable though holds the perceptron, but this is not in a trained state. So this is in a created state, but this is not in a trained state. Now to train it, we will need a few more steps. So this will not give us the correct result, but this is the way how to create a perceptron, and how to use it step by step. So here the same thing, we can define the target. Now one more thing is that we should train it. So therefore, since there in that case we were not training it, therefore we want to see what the response shall be while we design the perceptron. So if we want to see what the result shall be, there is the result before training. Now, if we want to train it, we need to make some changes. We will say that here we will use a 20 session, a 20 cycle session for doing the training. So here we write it like this: net.trainparam.epoch is equal to 20. So 20 such sessions training cycles will be run, and then we will run here a training by the use of this built-in function train net. That same net variable now will hold the variable once we complete the training. So train net p, net comma p comma t. So this will be the training. So both p and t now will so both t and p will be now be here taken. Since p here is the pattern, t here is the training, so they will or will take part in training for 20 cycles. So once the training part is complete, we can write one more time y is taking the value of net from the trained net structure, and then taking a pattern vector p. So here is the result. So y shall be equal to 1 1 1. That is same that we want. So if we now see this thing, how the network behaves, a structure of that type shall be generated simultaneously. That will tell us the number of iterations required. There it's 3 iterations, the time taken, and the performance say goal reached. That is the performance goal. Means the gradient descent, the difference, the gradient has descended to zero value at 3 number of iterations, and at that state we find that y has generated the targets perfectly. So this can be seen, and we can track the training and see or visually verify the changes that have taken place while we design or run the perceptron. Now we can also do here a linear classification, since we have spoken about linear classification previously. So we can do here a linear classification by the use of a simple discriminant function that looks like this, can be represented by the purely built-in function. So here shall be the pattern and target, pattern and target, pattern and target, pattern and target. So for these particular patterns, P1, since P will be the pattern vector, and P1, P2, P3, P4 shall be the subset of the pattern vector, while T1, T2, T3, T4 will be the subset of the target vector. So that way we can fix the pattern and target. So we take a net variable that will hold a structure generated by the newly built-in function that takes these values. So the significance is that it will take values ranging between -2 and 2, and the weights to start with will have values between -2 and 2, and there will be one neuron. So there will be one neuron, and while we train the network, train that linear classifier or the linear discriminant function, we have set a training goal of 0.1, and then we can carry out the training. So that will be the training. So once we do the training and see what the result is, we need to store the train network variable at this net variable, and then retain some of the training performance parameters at TR, while we take pattern and the target vector simultaneously. So once we run the training, it will look something like this. And we find that beyond 64 number of cycles run, we see that the performance goal is met. So the performance goal is met. So no further training will be done. So once we do that, we will see that that if we do a we see the result from the system, we can write sim bracket net comma p. That means we use the train variable net and give the pattern vector p. We'll find that particular result coming out. So so this might not be very close to what we want. That means we need to train it more. So we need to train more. So we need to make this goal further less. So if we make this goal further less, this training will run for more number of cycles, and if it runs more number of cycles, this particular value will be closer to what we want, to that particular value. Now, if you can do a thresholding, you can see that particular value can be thresholded to 0. That particular value can be thresholded to 1. That particular value can be thresholded to 0, but this value cannot be thresholded to 1. So there are problems here. Therefore, we need here more number of cycles. But this is a very simple way to do a linear discriminant function, or generate a linear discriminant function by following the next stages of the perceptron design. Okay. Now you can use a GUI also to create a perceptron. So you can use that GUI. So that particular GUI is quite flexible, very much flexible. It looks something like this. So what are the patterns you want to give? What is the network you want to select? What will be the targets? If you want to give some delay states, you can also give that layer by layer, so on and so forth. You can read the data from your computer's disk directly. So once you read the data from the computer's disk, it can give you lots of flexibility to read a different type or wide variety of data, and then use the data to train the network. So once you can once you select these things, you can further select the transfer function, the number of neurons you want, number of layers you want to have there, many things. So you can all figure out that, and then once you figure out these things, you can train the network and then finally generate the response that you want. So the window, you can see that can come step by step. So data 1, so you can read some data or type there some data and save it with a data variable. You can create your own network and give it a name, and then specify its or give its own specification, or fix its own specification. So once you fix the specification, it can be saved so that you can use it sometime later. So you can put a name here, and then that way develop it. Now let's come to supervised learning and then see how we can create a multi-layer perceptron. Now we have talked about that in case of the multi-layer perceptron, the same perceptron concept comes, but here you will now use many perceptrons, but those will be grouped in layers: layer 1, layer 2, layer 3, mostly 3 layers. One will be the front end, one will be a middle layer, and one will be at the back end. So you will feed the patterns from the front end. The middle layer will be doing the mapping from the front end to the back end, and then in the back end you will be generating the response. Now while the patterns coming from the front end and going to the back end, the mapping part is done during the training. Training is based on the back propagation mechanism. So now let's see. So steps of backpropagation, very simple. You need to first select a set of random weights for all the connections layer by layer. Then you can select a pattern X, then propagate the signal through the network, compute layer by layer the values, and finally you will get one O that at the last end of the network. Then you need to find out a del, that is the gradient function. So the difference between what you want currently and what is the current response from the network. Small difference between these two, the rate of change of the small difference compared to the weights, that is the gradient. So this particular value needs to be calculated, and depending upon how this gradient changes, shows you a descent, a decrease, you need to tune the weights W. So this particular process goes on repeatedly, layer by layer. That will be crucial in calculating the most precise weight values, for which the final response of the network becomes very close to what you want. Okay. So there is one case, very simple case. Let's see. Now here there is a pattern that you have a set of values, a 2x4 matrix. So the target is here -2, -2, 1, 1. Now this particular built-in function new double f that will be creating a new feed forward network that takes values. Now this min max will be returning a matrix that will have the minimum and the maximum range of values that the pattern vector will have. Here we need it to tell the network beforehand that you are supposed to deal with values in this particular range. Now next particular thing is 5. So there will be 5 neurons in the middle layer, and there will be one neuron there at the last layer. So just coming back to the previous slide, we can see now here there is one middle layer. Here we are showing 2, but there are no 2. There is one layer, middle layer. So here there shall be 5 number of neurons, and there will be one neuron here finally. So this is the structure that this will be creating. Now this particular 10 sig is a 10 sigmoidal function. So in the 5 in the middle layers, that you will have here 5 numbers of 10 sigmoidal transfer functions, 5 numbers of 10 sigmoidal activation functions. Then in the last layer, you will have one purely linear transfer function, activation function, and finally there is the training type. You see here train GD. So that means you will use here a backpropagation method of training that is called gradient descent. So that one is the most rudimentary form of gradient descent backpropagation training. So it's called train GD. So this particular train GD function is used. That is a built-in function. We will speak about the different varieties of built-in functions that are there in the Matlab toolbox, neural network toolbox. We will speak about that in the next class. But now you become familiar with it, that this is a very rudimentary form of gradient descent function called train GD. This particular train GD can be given some some training time parameters. Here is first of them, net.train param. So that means when you complete 100 number of iterations, you can display the result. Then you are fixing here a learning rate. This is a learning rate 0.045. If you have a big, I shall speak about the learning rate later on. If you have a very big learning rate, your system might not be a stable one, but the learning shall be fast. And while you have a very small learning rate, that may take time, but your learning shall be stable. Your learning shall be more precise. Now you will run the training till up to 300 number of recursions. You have fixed a training goal of 10 to the power minus 5. So your difference must fall down to 10 to the power minus 5 level. So small. Then finally you will be simulating the result. So now while you run the training, you will find that once you complete 79 number of the epochs, you will find that the training goal is reached. You have reached a gradient descent difference that has a value of 10 to the power minus 10. So sufficient amount of precision has been generated. The training is quite good, and you have reached the training parameter or the training time goal. Now see what are the results. Now, if you can round it off, that will be 2. You see that is the 2. This is 2 already. Round off that one, that will be 1. That round it off, that one shall be also 1. So you can see that the network has reached a goal. So this particular network structure for this particular pattern mapping is quite successful in generating the desired level of reliability, and we have seen that this particular network works well and have reached a target quite fast, just about 79 number of epochs. Okay. Now this particular network will look like this. So here there was a 10 sigmoidal transfer function in the middle layer, and in the last layer you have a purely linear function. So while you design this particular network, this sort of a vision must come to you. So how the Matlab working logic is translated to the code, this particular diagram summarizes it. So this particular train function that was key for doing the training has several parameters. Syntax is something like this. It can take so many variables and can also return so many. So it will take mainly the net variable that was seen previously, how we can define the net variable. You can take the pattern, you can take the target, and many further. EI will be the initial delays that you can have. If you do not want to have, those will be default zeros. Then you can have AI, some of the delays. I shall speak about the delays later on while we speak about the dynamic types of the A and N. Then I shall speak about why we need the delays. So here in our case, we are not dealing with the delays, so therefore we have not shown the delay part. And then sometimes you have lots of data, therefore you want to have certain validation checks, therefore you need to have the validation vectors. Then you can have some test vector structures too. Then you can have mostly two number of variables as the returns. One shall be the train network structure, and then the TR, that will be the training record, number of epochs completed, and the and the performance generated, or that is the learning descent, or the gradient descent performance. Then rest are if we need at some point of time. So here is the required multi-layer perceptron that we just saw. That will be the conceptual diagram that will be used by the Matlab compiler repeatedly while you use the new FF function. Okay, so now let's see how a two-layer network will look like. Same thing, but now we can see that here we have used two middle layers. One has 5, and one layer has 10 number of neurons. So one has used the 10 sigmoidal function. The second layer to also use all the 5 number of 10 sigmoidal transfer functions. Next layer also uses 10 number of 10 sigmoid functions, and last one uses the purely linear function. And we here report one more function called the train GDA, that where you have an a learning rate, that is the adaptive learning rate. That particular learning rate will vary as per the requirements. We will speak about that in the next class. So train GDA, where you have an adaptive learning rate. So rest are same, and rest of the methods are, or rest of the conditions are same. But here we have used a two middle layer structure. And the two middle layer structure will normally show you better learning. So now, while we have spoken about the back propagation, you should remember there are two modes of back propagation. One is called the batch processing training, and the second one is called the sequential training. Now, rest of the back propagation things are since we have discussed, we will skip it. Let's come to these two modes of training. Now, in the batch mode, the weights and the biases of the network shall be changed or shall be tuned when you have the complete set of training given to the network. So once you give the complete set of patterns and targets to the network, you will change the weights and the biases. So in one cycle, when you complete one recursion, you will give the complete set of weights and biases to the network, and then you will make variation to the weights of the network. That is the batch mode of training. Now, in the sequential mode, you will give one set of patterns and one set of class codes. So the class codes and the pattern codes will come in a sequence 1, 2, 3, 4. So class 1, class 2, class 3 pattern, or the first pattern comes, second pattern comes, third pattern comes. So these will come in a sequence, and in the sequential mode, while you feed the patterns and targets one by one, weights and biases of the networks will be modified or updated, I mean, each time. So there is a difference between that. But normally, the more common mode of training is the batch mode of training. Now let's come to a few very specific cases where you can use the multi-layer perceptron for real life situation. One very simplistic uh, structure can be used for designing a data compression and decompression system. So you can have here a data compression system. So supposedly you have a system where there are n number of patterns. So n number of patterns, if you want to compress it, or you want to uh, group them into compressed representations, these number of patterns can be compressed to m numbers. So m will be smaller than these n. So this will be the compressed form. So here what we can do is that in the multi-layer perceptron, so here we need to give the n, and here we will give the m. So the representation of the compressed form, or the compressed representation m, shall be there. There the back end, the lesser numbers shall be there, and the front end, the bigger numbers shall be there. So if that part is 1000, we can make it 500, or we can make it 200, 100. So this will lead to a compression generated. So the network now can generate a compressed representation. Now that particular compressed representation, from that particular compressed representation, can be again used to recover back the previous form. So from this m, we can recover back the n by doing just a reverse processing, by just doing a reverse processing. So if you have a compression done at the transmitter side, just a reverse process should be done at the receiver side. So this particular n to m, then again m to n, this is a very delicate representation. A compression, decompression can be done by the use of the multi-layer perceptron. Then one more thing, you can use the multi-layer perceptron for the time series prediction. Yes, time series prediction, you can find the similarity in the prediction of the weather, climate, stock market, share prices, currency rates, so on and so forth, and passenger surge prediction, and so on and so forth. Now you can do time series prediction. Multi-layer perceptron can be used for the purpose, but multi-layer perceptron will not give you very reliable results. So you can try, but it will not give you very good results. For generating very good results from the time series prediction, you need to have a feedback network. So for time series, though multi-layer perceptron was used for time series prediction, later on people found that feedback networks are very good for doing the time series prediction. Then OCR is the most popular application of the multi-layer perceptron. So in the design of the OCR, you have the data collection, configuring the network, training and testing. So this was done all throughout the previous four or five decades very successfully to make the 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 technology reach a very steady or stable level, or a very reliable level. So the process can be something like this. You have a training stage, you have a testing stage. So in the training stage, you read the patterns, you do pre-processing, you do segmentation. Segmentation means word from the sentences, words will be segmented out. From the words, you will be segmenting out the characters, and once you have the characters, you will be doing a feature selection, feature extraction. Then you will be training a classifier that will generate the class codes. Now the same now this will be done during the training. Now the same flow shall be seen in the testing part also. Same flow, classification will be shall be done, and once you have the classification code, the classification code will be compared with the classification code generated during the training, and the best match will lead to the uh, recognition decision. So this way, the OCR technology has developed, or will function, or will work. So you can see that the ANN is is preferred for this sort of uh, task, mainly for its flexibility, its ability to learn multiple features, can learn multiple classes, deal with the multi-class problems, can deal with the variations that shall be there in the patterns, and that way function in a robust manner to give the decision despite the character sets showing multiple variations. So you can for this particular class, we have shown here a big size of classes. So this may not be the limit. You can have more number of classes, 100 classes, 90 classes, 100 classes, 500 classes. No such limitation. But previously people followed a norm that for one class you need to have minimum two number of features. Therefore, if you have say a class set of 100, you need to have a feature length of more than 200, double that particular figure. So here is one such case, a configuration for these number of classes. How you will configure the the mm, say middle layers, first middle layer, second middle layer, third middle layer. That way you can select, configure. Backpropagation will come. Then there are works reported by a Spanish group where they have used the multi-layer perceptron to generate solar radiation maps in Spain. So they have taken data from a number of years for a number of years, and this particular group reported a study that was carried out for about 30 years, and they took all the reading, geographical reading of the solar light distribution in all of Spain, and then they took the data specifically for six number of cities, and then generated uh, a a prediction that has a step size of 1 hour, 1 hour duration. So 1 hour basis, the sunlight falling on particular city, they could give a prediction. So they could give a prediction on an hourly basis for the solar light or solar radiation falling on six different cities. So this was a fantastic work, a nice scientific work that showed great reliability, and they have reported the use of multi-layer perceptron. Then our defense forces need lots of support, mainly to do work. They're in the fields. They're in the war. They're in the different geographical locations to say prepare for war or for defense of our countries. So they can also use the multi-layer perceptron to have a prediction or a visual regarding the terrain on which they are likely to work, likely to be deployed. So you can see that here is one such network structure which reads values of forests, road, build up locations, slopes, and all that. They took a total of 61 pattern types, and those values were taken from satellite data. So from satellite data, they could read these values and feed to multi-layer perceptrons, and then they could generate a particular terrain map which are known to them for a particular reason on which they are deployed. So beforehand, how that particular uh, terrain will have variation in the springtime, rainy season, um, say the snow falling time, winter time. So in all these different times, different circumstances, say the traffic rising, people coming in large numbers, people are in lesser numbers. So for all those variations, river flowing in full flow, then sun glowing in full light, sun less glowing, then storm coming, all those situations, they need the know-how. They could generate a picture beforehand of a particular terrain, and they could do it by the use of the multi-layer perceptron. So this work is quite successful, very well reported. Then you can you can find people reporting the use of multi-layer perceptron for vision problems. Vision problem means recognition of vehicles, uh, recognition of say military vehicles. So they have now this particular structure is quite a complex one. They have grouped multiple numbers of multi-layer perceptrons, and those multi-layer perceptrons, they will all receive the feeds of all those vehicles. So one particular block is meant to detect one class. So this particular block is supposed to detect this particular class. This particular block is supposed to detect this class. This particular block is supposed to detect this class. So they will all detect, since the feature fed is a common type. So they will use a decision combination by a voting, uh, say maximization of the detection probability based on a voting they will use. And for this particular class, this particular network will generate maximum likelihood probability of detection of correct decision. Then they have further used more number of features, and then reinforce the decisions that have come from this particular structure. So to make the decision very strong, to make the decision very reliable, to make the decision very say fruitful, they have combined multiple number of multi-layer perceptrons in different configurations and have reinforced their decisions. Then then people have reported the prediction of thermal conductivity by the use of multi-layer perceptron. You see the versatile mm, say versatile nature of the multi-layer perceptron. People have used the multi-layer perceptron for doing detection, prediction, regression of thermal conductivity of liquid solutions. So here are some of the structures. There are multiple number of neurons fed at the front end. The different uh, values layer by layer they have shown here, and that way they have shown a 90% 90% reliability for doing detection of thermal conductivity of certain electrolytic solutions. So that is a mark of the reliability of the multi-layer perceptron and its popularity for a range of scientific purposes, for scientific research. Now the big thing is that big difficulty is that multi-layer perceptrons, though are quite successful, but have remained confined to software domains only. The uh, the physical designs of multi-layer perceptrons have largely been trouble domains. The physical structures have not been fully designed successfully in a very large manner. Though there are reports of people generating VLSI-based multi-layer perceptrons, the field programmable grids are used for design of multi-layer perceptrons, but the progress or the popularity of the design of the multi-layer perceptron, as it is in the software domain, that same thing is not seen or replicated in the physical design domain, in the hardware domain. That is not the same case. But now people have reported the use of multi-layer perceptron or the design of multi-layer perceptron with MEM resistive crossbar circuits. Now here there is a person from Russia. So I don't know much regarding this person, but this work was reported in a very reputed journal just a few months back. But they have done a very good work, reported it, and they have used a passive MEM resistive crossbar circuits to design multi-layer perceptron structures. If that is done very successfully in a very smaller scale, our goal to reach through AI-based devices, components in the physical form, in the hardware form, shall be very much realizable. Now all the AI based structures are roughly software based. But if these sort of works can become successful, we will find our smartphones possessing through AI driven processors, through AI driven GPUs, through AI driven multimedia cards. So that will lead the device design to a new level. So that will be the true birth of AI based physical structure designs, physical designs. So here is one such work, very well written, very well documented, and the work is sound, very sound. The practical work is quite sound. Then you can find the multi-layer perceptrons quite well used for doing data mining. Data mining means you want to have content, content retrieval, you want to locate content, you want to find where it is, if there are manipulation changes, all those things, breach of security, if there are changes, if there are if you need to have a validation check of documents, of data, means all those cases where you need data mining, the support can come from multi-layer perceptron, because it can read data patterns quite well. It is uh, uh, quite reliable in relating patterns to classes. Therefore, it is quite successful, or it is quite successfully used for data mining situations, purposes. So I will here summarize. So Matlab is a reliable tool for teaching and learning that is based on visualization. Most of the Matlab teaching learning is menu driven. Then you can use the Matlab to design a the neural structures, ANN. Then for the perceptron, multi-layer perceptron, so on and so forth, there are huge amount of supports in Matlab, and you can derive lot of neuro computing structures and applications by the use of the Matlab. So I would now here is that reference which you can all follow. Simon Akin's book. It's like the Bible. And before I close, I would like to request spectators to raise questions. I shall be pleased to reply your queries. So I shall be sharing the slides, and I shall be sharing the recording also. And if you have some doubts, you can still raise the doubts and contact me. I find somebody keen to raise one point. Try. I shall share the slides. I shall share the slides. Don't you can be sure I shall be. There is one question from Saruk. Saruk is from my state. So I would like to. He has raised one point. The most comfortable for a beginner to practice ANN. I would say that Matlab is the more comfortable tool to start with. So once you become comfortable in Matlab, I would suggest you to shift to shift to Python. Matlab for the beginner to deal with these learning systems is quite supportive, quite good. So you can start with the Matlab part. That will be good for you. You have lot of support. Documentation is quite good. Built-in functions are there. Lots of built-in functions. Your task will be simplified, and once your task is simplified, your learning becomes good. So when your learning becomes good, your confidence grows, and confidence is a very good thing to have in the student days, because it drives the learning part. It will permit you to learn more things. So therefore, to start with, you can begin with the Matlab. Matlab is the most popular tool worldwide. So Matlab is therefore the more preferred choice. So I think Sriyak was trying to raise a question. If I am not wrong in my spelling or pronunciation, Krayak, I think I should pronounce Krayak. So if you want to raise one question, please raise. I shall be keen to reply. So I think there are no further questions. So I shall be sharing all these slides to Dr. Kaplan. So he will be giving it to you. So with these, we will close this session. We'll meet one more time on Thursday, and there I shall be speaking about more and more different techniques of how to train the neural networks. You will learn more and more about its training parts. So yes, thank you. Thank you.
Thank you, Professor Sarma.